Before you, before the earth, before the sun and the stars themselves, there was a single moment that contained everything. You want to know the universe's ultimate origin story? We're told it all started with a bang. But the quiet truth is, it was probably much stranger, much quieter, and infinitely more mysterious than that. So before we can journey to the Big Bang itself, we must first appreciate how we even know it happened. The idea of a universe with a beginning is actually very new. For most of human history, it was assumed that the universe was eternal, static, and unchanging. But in the early 20th century, a series of quiet discoveries began to unravel that ancient idea, leaving us with a much more dynamic and fascinating picture. These are the clues that form the foundation of our entire cosmic story. Our first clue, the one that blew the whole case wide open, is the simple fact that the universe is expanding. This story begins in the 1910s and 20s with an American astronomer named Vesto Slipher. He was using the powerful new telescopes of his day to study what were then called spiral nebulae, faint, fuzzy patches in the sky. He was measuring their light spectra, and he found something very strange. Almost every single one of these nebulae was redshifted.
Now, redshift is just a simple consequence of the Doppler effect, something you experience every day. When an ambulance siren is coming towards you, its pitch sounds higher. As it passes you and moves away, its pitch suddenly drops and sounds lower. The same thing happens with light. Light from an object moving away from you gets stretched out to longer, redder wavelengths. Light from an object moving towards you gets compressed to shorter, bluer wavelengths. What Slipher had discovered was that almost every galaxy he could see was moving away from us at incredible speed. This was a profound and puzzling discovery, but it was the work of Edwin Hubble in the 1920s that turned it into a revelation. Hubble, using the massive Hooker telescope on Mount Wilson in California, was not only able to confirm Slipher's findings, but he was able to measure the distances to these galaxies. And when he plotted their distance against their speed, he found a stunningly simple and powerful relationship. The farther away a galaxy was, the faster it was moving away from us. This is now known as Hubble's law. This discovery completely changed our understanding of the universe. It meant that the universe was not a static, unchanging place. It was dynamic, and it was getting bigger. And this is where the famous raisin bread analogy comes in. Imagine our universe is a loaf of raisin bread dough. The raisins are the raisins. As you bake the bread, the dough itself expands. From the perspective of any single raisin, all the other raisins would appear to be moving away from it. And a raisin that is far away would seem to be moving away much faster than a nearby raisin, because there is more expanding dough between them. This is exactly what we see. It's not that we are at the center of a great explosion and all the galaxies are flying away from us. It's that the fabric of space itself is stretching everywhere at once, carrying the galaxies along with it. And this has a profound implication. If the universe is expanding now, it means that in the past, it must have been smaller, denser, and hotter. If you run the movie of the cosmos backwards, everything eventually converges to a single, incredibly hot, incredibly dense point. This was the first great clue, the first quiet whisper of a moment of creation.
The second great piece of evidence for the Big Bang was discovered completely by accident, a beautiful story of scientific serendipity. Our story moves to 1965, to two American radio astronomers named Arno Penzias and Robert Wilson. They were working at Bell Labs in New Jersey with a large, horn-shaped radio antenna. They were trying to use it for radio astronomy and satellite communication, but they kept running into a problem. No matter where they pointed their antenna in the sky, they picked up a faint, persistent, and incredibly annoying background hiss, a low-level static that they couldn't get rid of. They tried everything to eliminate this noise. They thought it might be an issue with their equipment. They rewired their receivers, they checked all their connections. They even famously climbed into the giant antenna horn with brooms and scrub brushes to clean out what they called a white dielectric material, more commonly known as pigeon droppings, thinking it might be the source of the noise. But nothing worked. The quiet, gentle hiss was always there, coming from every single direction in the sky, day and night, season after season. At the same time, a team of physicists at nearby Princeton University, led by Robert Dicke, had come to a theoretical conclusion. They reasoned that if the universe had begun in an incredibly hot, dense state, then the radiation from that initial fireball should still be detectable today. It would have cooled down as the universe expanded, and its light would have been redshifted all the way down into the microwave part of the spectrum. They were, in fact, in the process of building their own antenna to try and find this ancient afterglow. When Penzias and Wilson happened to hear about the Princeton team's work, they had a stunning realization. The persistent, annoying hiss that they had been trying so hard to get rid of was not a problem with their equipment. It was the echo of creation. It was the oldest light in the universe. They had accidentally stumbled upon the cosmic microwave background, CMB.
This discovery was a monumental confirmation of the Big Bang Theory. The CMB is, in essence, the baby picture of our universe. It is a snapshot of the cosmos as it was just 380,000 years after the Big Bang, at the moment it first became transparent. Before that, the universe was a hot, opaque fog of plasma. The CMB is the light from that ancient wall of fog. When we map this light with our modern, sensitive satellites like the Planck spacecraft, we see that it is almost perfect uniform. The temperature is the same in every direction at a steady 2.725 Kelvin, just a couple of degrees above absolute zero. But there are tiny, almost imperceptible fluctuations in that temperature, differences of only 1 part in 100,000. These tiny ripples, these slightly hotter and slightly cooler spots in the baby picture of the universe are incredibly important. They were the primordial seeds, the tiny density variations that gravity would later act upon to grow all the structure we see in the universe today. Every galaxy, every star, every planet owes its existence to one of these tiny, quiet fluctuations in the ancient light. The CMB is the second great pillar of evidence, a beautiful, silent, and all-pervading echo of a hot, dense beginning. Now we come to our third and final clue, a piece of evidence that is written into the very chemical composition of the cosmos itself. This is the mystery of the abundance of light elements. Our modern understanding of how stars work tells us that they are fusion engines. They forge heavier elements in their cores. But when we look at the oldest stars and the most pristine gas clouds in the universe, we find that they all have a very specific, uniform chemical recipe. They are all made of about 75% hydrogen, 25% helium, and tiny trace amounts of lithium. Why the specific ratio? Why 25% helium everywhere? Stars alone can't explain this.
The Big Bang Theory provides a perfect and beautiful explanation. It predicts that in the first few minutes after the Big Bang, the entire universe was so hot and so dense that it acted as a single colossal fusion reactor. This process is called Big Bang nucleosynthesis. Let's imagine the scene. From about 3 minutes to 20 minutes after the beginning, the temperature of the entire cosmos was about the same as the core of our sun. It was a universe-sized star. In this cosmic kitchen, the protons and neutrons that had formed in the first second began to fuse together. Protons and neutrons would fuse to form deuterium, or heavy hydrogen. Then deuterium nuclei would fuse to form helium-3, and then helium-4, the most common isotope of helium. The theory makes an incredibly precise prediction. It says that by the time the universe had cooled down enough for this fusion to stop, about a quarter of all the normal matter in the universe should have been converted into helium-4. And this is exactly what we see. The fact that the oldest, most pristine parts of our universe have this specific 25% helium abundance is a stunning confirmation of the Big Bang model. It is the chemical fingerprint of the first few minutes of time. So, with these three great pillars of evidence in place, the expanding universe, the cosmic microwave background, and the abundance of light elements, we can now begin our journey back in time with confidence. We are going to rewind the cosmic clock past the galaxies, past the first atoms, past the first protons and neutrons, all the way back to the very first, most mysterious moments of our universe's existence.
All right, let's take a deep breath. The journey we are about to take is a journey into a world of physics and scales that are almost beyond our ability to describe. The first second of the universe's life was the most violent, most energetic, and most important second in all of history. It was in this single brief instant that all the laws of nature and all the matter and energy we see today were set in place. We will walk through it slowly, era by tiny fraction of a second era. Our journey begins at the very beginning. We are at level 71, the Planck epoch. This is the earliest moment in time that our current laws of physics can possibly describe. It is the period from time 0 to about 10 to the power of minus 43 seconds after the Big Bang. That's a decimal point followed by 42 zeros and a 1. It is a timescale so incredibly short it is meaningless in human terms. In this epoch, the entire observable universe was a region of space far, far smaller than a single proton. It was a point of almost infinite density and infinite temperature. And at these extreme energies, our two best theories of the universe, general relativity and quantum mechanics, break down. They give nonsensical answers. To truly understand the Planck epoch, we would need a theory of quantum gravity, a theory of everything which we do not yet have. So this first moment is the ultimate mystery. It is a quiet wall beyond which our current science cannot see. But we believe that in this state the four fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces, were all likely merged into a single, unified superforce. It was a moment of perfect, unimaginable simplicity. As the universe expanded and cooled ever so slightly, this perfect symmetry began to break. This brings us to our next era, the Grand Unification Epoch, or UGT epoch, at level 72. This period lasted until about 10 to the power of minus 36 seconds. At this point, the universe had cooled just enough for the force of gravity to freeze out and separate from the other three forces. The strong and weak nuclear forces and electromagnetism, however, were still merged together into a single unified, grand unified theory force. The universe was still a seething soup of exotic, fundamental particles that we have never seen in our modern, cooler universe. And it was at the end of this epoch that the most important and most dramatic event since the beginning is thought to have occurred. This brings us to level 73, cosmic inflation. As we discussed, the theory of inflation was proposed to solve some of the deep paradoxes of the Big Bang model. The idea is that at around 10 to the minus 36 seconds, the universe underwent a period of incredible, mind-boggling exponential expansion. It was driven by the energy of a hypothetical inflaton field, a kind of energy inherent in the vacuum of space itself. For a tiny, tiny fraction of a second, the universe grew in size by a factor of at least 10 to the power of 26. That's a 1 followed by 26 zeros. It went from being a region of space far smaller than a single atom to being about the size of a grapefruit, almost instantaneously. This expansion was much, much faster than the speed of light. Now, this doesn't violate Einstein's theory because it wasn't matter moving through space faster than light. It was the fabric of space itself that was stretching. It was a moment of incredible, almost violent growth. This inflationary burst is what took the tiny, subatomic, uniform patch from the Planck epoch and stretched it out to become our entire vast observable universe. It's the event that smoothed out the cosmos and made it flat, solving the great paradoxes of our baby picture of the universe.
After this brief, incredible burst of inflation was over, the universe settled down into a more sedate, but still incredibly hot and dense period of expansion. The energy from the inflataton field was converted into a seething hot soup of fundamental particles. This brings us to level 74, the quark-gluon plasma. From about 10 to the minus 12 seconds after the Big Bang, the universe was so hot, trillions of degrees, that not even protons and neutrons could exist. It was a sea of their constituent parts, quarks and gluons. Quarks are the fundamental particles that make up protons and neutrons, and gluons are the particles that glue them together, the carriers of the strong nuclear force. In this early state, they were all free, a hot, dense, and almost perfect liquid, churning and interacting with electrons, photons, and other exotic particles. It is in this primordial soup that another of the universe's deepest mysteries is thought to have occurred. This is level 75, baryogenesis. The laws of physics as we know them are almost perfectly symmetrical when it comes to matter and antimatter. For every particle, there is an antiparticle with the opposite charge. When matter and antimatter meet, they annihilate each other in a flash of pure energy. And when energy converts into matter, it should create an equal amount of matter and antimatter. So, in the early universe, there should have been an almost perfect balance between the two. But if that were the case, as the universe cooled, all the matter and antimatter would have annihilated each other, leaving behind a universe filled with nothing but light. But that's not what we see. We live in a universe made almost entirely of matter. For some reason, there was a tiny, tiny imbalance in the very beginning. For every 1 billion antimatter particles, it's thought there was 1,000,000,001 matter particles. After all the annihilation was over, that tiny little leftover fraction of matter is what went on to form every star, every galaxy, and every one of us. What caused this crucial, life-giving asymmetry? We still do not know. It is one of the most profound, quiet questions in all of cosmology.
As the universe continued to expand and cool, it reached a point at about 1 microsecond after the Big Bang where it was no longer hot enough for quarks and gluons to exist freely. This brings us to our next stage, at level 76, the Hadron Epoch. During this epoch, the strong nuclear force became powerful enough to bind the quarks together, forming the first composite particles we would recognize. These are the hadrons, which include the protons and neutrons that will make up the nuclei of all future atoms. The universe was now a dense, hot soup of protons, neutrons, electrons, photons, and neutrinos and their antiparticles. The annihilation of matter and antimatter was still happening at a furious rate, but because of that slight asymmetry we just discussed, the matter particles were winning. The temperature was still too high for protons and neutrons to bind together to form atomic nuclei. Any that did would be instantly blasted apart by a high-energy photon. The universe was still a chaotic, energetic place, but for the first time, the fundamental building blocks of the matter we know today were beginning to take shape. It was a quiet but crucial step in the cooling and ordering of the cosmos. And with that, the most dramatic, most energetic, and most mysterious first second of the universe's life comes to a close. What follows is a much slower, but no less important period of cosmic creation. We now enter a new phase in our journey. The universe is a few minutes old. It has expanded and cooled considerably, but it is still incredibly hot and dense, much like the core of a star. And for a brief period, the entire universe will become a single, giant nuclear furnace. This is the era of Big Bang nucleosynthesis, which is our level 77.
From about 3 minutes to 20 minutes after the Big Bang, the conditions across the entire cosmos were just right for nuclear fusion to occur. The temperature had dropped to about 1 billion degrees Kelvin. At this temperature, it was no longer so hot that any newly formed nuclei would be instantly destroyed, but it was still hot enough for protons and neutrons to overcome their electrical repulsion and fuse together. The process began with the protons and neutrons that had formed in the Hadron epoch. They began to fuse together to create the first complex atomic nuclei. A proton and a neutron would fuse to form a nucleus of deuterium, also known as heavy hydrogen. Then, 2 deuterium nuclei could fuse to form a nucleus of helium-3, or a deuterium nucleus could fuse with another proton to also form helium-3. Finally, 2 helium-3 nuclei could fuse together to form the very stable and common isotope helium-4, which consists of 2 protons and 2 neutrons. This process was incredibly efficient. By the end of this 20-minute period, almost all of the free neutrons in the universe had been locked away inside helium-4 nuclei. The theory of Big Bang nucleosynthesis makes an incredibly precise prediction. It says that the final composition of the universe by mass should be about 75% hydrogen nuclei, which are just single protons that didn't find a partner, and about 25% helium-4 nuclei. And when we look out at the oldest, most pristine parts of the universe, like ancient gas clouds that have not been contaminated by stars, this is exactly what we find. The chemical composition of our universe is a direct, quiet fossil from this cosmic kitchen phase in the first few minutes of time. This perfect agreement between the theory and observation is one of the most powerful and beautiful pieces of evidence we have for the entire Big Bang model. It's a quiet whisper from the dawn of time, telling us we are on the right track.
Now, you might ask, why did the process stop there? Why didn't the universe continue to fuse helium into carbon and oxygen and all the other heavy elements that we see today? This brings us to level 78, the lithium problem and the end of fusion. There are 2 main reasons why Big Bang nucleosynthesis created almost nothing heavier than helium. The first is something called the deuterium bottleneck. Deuterium, that nucleus with one proton and one neutron, is a crucial stepping stone in the fusion process. But it is also very fragile. In the very hot, early moments of nucleosynthesis, it was difficult for deuterium to survive long enough to form heavier elements. But the bigger problem was the lack of stable nuclei with a mass of 5 or 8. If you try to fuse a helium-4 nucleus with a proton, you get a lithium-5 nucleus, which is incredibly unstable and decays almost instantly. If you try to fuse 2 helium-4 nuclei together, you get a beryllium-8 nucleus, which is also incredibly unstable. Because there are no stable rungs on the elemental ladder at mass 5 and 8, it was almost impossible for the early universe to build up to heavier elements like carbon. The process essentially got stuck at helium. It did manage to create tiny trace amounts of lithium-7, but that was about it. All the heavier elements that make up our world and our bodies, the carbon, the oxygen, the iron, had to be created much, much later in the fiery hearts of stars and in supernova explosions. And this brings us back to that quiet, nagging paradox we discussed earlier, the cosmological lithium problem. While the Big Bang Theory perfectly predicts the amount of hydrogen and helium, its prediction for lithium is off by a factor of 3. We observe less of it in the oldest stars than the theory says should be there. It's a small, subtle, but persistent crack in our otherwise perfect picture of the early universe, a quiet reminder that there are still mysteries to be solved, even in the first few minutes of time.
All right, let's take another slow step forward in our cosmic story. The first 20 minutes are over. The universe has its primordial recipe of light elements, but it is still an incredibly strange and alien place. For the next few 100,000 years, the universe will be a hot, dense, and completely opaque fog. And at the end of this era, the single most important visual artifact of our cosmic history will be released. Let's explore this time, beginning at level 79, the opaque universe. For the first 380,000 years of its history, the universe was filled with a hot, dense plasma of atomic nuclei, mostly hydrogen and helium, and free-roaming electrons. The temperature was still too high for these electrons to be permanently captured by the nuclei to form stable neutral atoms. In this plasma state, the universe was completely opaque to light. Light particles, photons, could not travel very far before they would bump into a free electron and be scattered in a random direction. It was like being in the middle of an incredibly thick, dense fog, or on the surface of the sun. If you were somehow able to exist in this early universe, you wouldn't be able to see anything. The entire cosmos was a single, uniform, glowing haze. But as the universe continued to expand, it continued to cool. And as the temperature dropped, it approached a critical threshold. This brings us to level 80, the moment of recombination. When the universe was about 380,000 years old, the temperature dropped to about 3,000 Kelvin. At this temperature, it was finally cool enough for the free electrons to slow down and be captured by the hydrogen and helium nuclei, forming the first stable neutral atoms. This process is called recombination. And in that moment, everything changed. With all the free electrons now safely bound up inside atoms, the photons that had been trapped in the plasma fog were suddenly free. The fog cleared. The universe, for the first time in its history, became transparent.
The light that was released at that exact moment of recombination is what we now see as the cosmic microwave background, CMB, which is our next stop at level 81. This ancient light has been traveling through the expanding universe unimpeded for the past 13.8 billion years. It is the oldest light we can possibly see. It is a surface of last scattering, a snapshot, a baby picture of the universe as it was in its infancy. When this light was first released, it was as hot and bright as the surface of a star. But over the last 13.8 billion years, the expansion of the universe has stretched its wavelength enormously. Its temperature has cooled from 3000 Kelvin down to just 2.7 Kelvin, just a couple of degrees above absolute zero. And its light has been redshifted from the visible spectrum all the way down into the microwave part of the spectrum. That's why we need radio telescopes to see it today. When we map this ancient light, we find that it is almost perfectly uniform in every direction, but it contains tiny, almost imperceptible temperature fluctuations, differences of only 1 part in 100,000. These tiny ripples are the most important things in the entire universe. They were the seeds of all future structure. The slightly denser, slightly cooler spots were the places where gravity would begin to pull matter together, eventually forming the first stars, galaxies, and galaxy clusters. We are, in a very real sense, looking at the blueprint for our own existence when we look at the CMB. After this great release of light, the universe entered a new and very different phase. This is level 82, the cosmic dark ages. For hundreds of millions of years, the universe was a quiet, dark, and relatively simple place. The initial brilliant light of the Big Bang had faded and redshifted away. The universe was filled with a vast, diffuse, and mostly uniform cloud of neutral hydrogen and helium gas, slowly and patiently clumping together under the gentle, persistent influence of dark matter. But there were no stars yet. There were no galaxies. There were no new sources of light at all. The universe had become a dark, transparent, and silent place. It was a period of profound cosmic quiet, the long dark intermission between the first act of the Big Bang and the second act, the birth of the first stars. This long, quiet night finally came to an end with our next level, level 83, the first stars, population 3. Sometime between a few 100 million to perhaps 1 billion years after the Big Bang, in the densest knots of the cosmic web, the clouds of hydrogen and helium gas had finally grown massive enough for gravity to take over and trigger their collapse. Deep inside these primordial clouds, the first stars were born. These first-generation stars, which astronomers call population 3 stars, would have been very different from the stars we see today. They were forged from the pure, pristine gas created in the Big Bang, almost entirely hydrogen and helium, with none of the heavier metal elements that our own sun contains. Because they lacked these heavier elements, which are very efficient at radiating away heat, the primordial gas clouds could not cool down as easily. This meant that they had to grow much, much more massive before they could finally collapse and ignite. So it's thought that these first stars were true titans, colossal spheres of hydrogen and helium, perhaps hundreds of times the mass of our sun. And because they were so massive, they would have been incredibly hot, incredibly luminous, shining with a brilliant blue-white light, and they would have lived very, very short and very dramatic lives. They would have burned through their fuel in just 1 million or 2 years, a mere blink of an eye in cosmic time, before exploding as spectacular supernovae. We have never directly seen a population 3 star. They are all long since dead, but we see their legacy everywhere, in the heavy elements they created and scattered throughout the cosmos. And the intense light from these first stars had a profound effect on the entire universe. This brings us to level 84, the epoch of reionization. As the first stars and small galaxies ignited,
They began to flood the universe with intense high-energy ultraviolet radiation. This powerful radiation streamed out into the vast dark clouds of neutral hydrogen gas that filled the universe during the cosmic dark ages. And it began to zap them, stripping the electrons from the protons and reionizing the universe, turning the neutral gas back into a hot plasma. This process didn't happen all at once. It started in bubbles of ionized gas around the first stars and galaxies. These bubbles then grew and grew, eventually overlapping and merging together until the entire intergalactic medium was once again a transparent ionized plasma as it remains today. This epoch of reionization was the final great phase transition of our universe. It marked the end of the cosmic dark ages and the beginning of the universe as we know it, filled with light, stars, and galaxies. When we look at the most distant objects we can see, like quasars that are over 13 billion light-years away, we are looking back to this very epoch. The light from these quasars has to travel through the remaining neutral gas clouds, and we can see the fingerprints of this reionization process in their light spectrum. It's like looking at the fog clearing at the dawn of cosmic time. Now let's turn to the objects that were born from this new light. At level 85, we have the formation of structure. The tiny density fluctuations we see in the cosmic microwave background were the seeds. The slightly denser regions had slightly more gravity. Over hundreds of millions of years, they began to pull in more and more material, first dark matter and then the normal hydrogen and helium gas. These halos of dark matter were the gravitational wells, the invisible scaffolding upon which the first galaxies were built. The gas that fell into these halos formed the first stars, and these small proto-galaxies then continued to grow and merge over billions of years, forming the large, majestic spiral and elliptical galaxies that fill our universe today. The beautiful, intricate structure of the cosmic web is the quiet result of gravity patiently amplifying the tiny, random quantum fluctuations from the very first moment of time.
And so, with the end of the cosmic dark ages and the birth of the great galaxies, we arrive in the modern universe. This is the stelliferous era, the age of stars, the era we find ourselves in today. For the past 13 billion years, the universe has been a dynamic and beautiful place. The cosmic web of galaxies has continued to evolve and grow. Inside these galaxies, generations of stars have been born, have lived their long, stable lives, and have died, enriching the cosmos with the heavy elements needed for new stars, rocky planets, and eventually for life itself. Our universe today is a place of incredible complexity and beauty, from the smallest asteroid to the largest supercluster of galaxies. We have developed the tools of science to piece together this incredible origin story, to read the ancient light from the dawn of time, and to understand the laws that govern it all. But our understanding, as we are about to see, is far from complete. For all that we know, the modern universe presents us with a series of deep, profound, and quietly unsettling mysteries. The more we learn, the more we realize how little we truly know. It's as if we have spent centuries building a beautiful, detailed map of our own small island, only to suddenly realize that our island is just one of countless others, floating in a vast, dark ocean whose true nature we do not understand at all. So for the final, highest levels of our journey tonight, we must leave the comfortable shores of established science and venture out into that strange ocean of the unknown. We are going to explore the great paradoxes, the bizarre theories, and the ultimate questions that lie at the very edge of our knowledge. These are the quiet, nagging whispers that remind us that the universe is and will always be more mysterious than we can imagine.
All right. Let's take a deep breath and ascend into a new, more abstract realm. We are now entering the Hall of Riddles, a gallery dedicated to the great paradoxes of the cosmos. A paradox is not a mistake. It is a quiet invitation to think more deeply. It is a beautiful, intricate knot in our understanding, and contemplating it is a wonderful, soothing exercise for a restless mind. We begin at level 81 with the most profound and most famous paradox of all, the great cosmic question mark that hangs over everything we have discussed. This is the Fermi paradox. As we have established, the universe appears to be a perfect place for life. Our galaxy alone contains billions of potentially habitable Earth-like planets. The chemical building blocks for life are everywhere, and the universe is very, very old, providing plenty of time for life to have evolved elsewhere, perhaps billions of years before life on Earth ever got started. So our galaxy should be teeming with life, and at least some of that life should have evolved into advanced technological civilizations. The galaxy is old enough that a single spacefaring civilization could have colonized the entire Milky Way in just a few million years. So the sky should be filled with their signals, their probes, their grand engineering projects. It should be a noisy, bustling cosmic metropolis. And yet, when we look and listen, we are met with a profound, unbroken, and what the scientists have called an eerie silence. This is the paradox in its simplest, most powerful form: the high statistical probability of extraterrestrial life versus the complete and total lack of any evidence for it. It is the simple, quiet, and deeply unsettling question: where is everybody?
The potential solutions to the Fermi paradox are a journey in themselves, and we have explored them in great detail before. Let's just quietly revisit the main categories of thought as we continue our ascent. The first category of solutions is the lonely one, the idea that the silence is because there is no one else to talk to. This is the realm of the Great Filter, a theory we'll place at level 82. This idea suggests that there is some step in the long journey from a simple molecule to a galaxy-spanning civilization that is so incredibly difficult to overcome that almost no species ever makes it past. This filter could be the origin of life itself, a near impossible chemical fluke. It could be the leap from simple microbial life to complex animal life. Or, in the most sobering version of the theory, the filter could be ahead of us, the idea that all advanced civilizations eventually destroy themselves with their own technology. Related to this is the rare Earth hypothesis, which we can place at level 83. This suggests there isn't one single filter, but dozens of smaller ones. It's the idea that for a planet to have the stability needed for complex life, you need a long, long list of lucky circumstances to all line up perfectly. The right kind of star, in the right part of the galaxy, with the right kind of unusually large moon to stabilize your climate. In this view, microbial life might be common, but worlds like ours are so fantastically improbable that we might be the only one in the entire galaxy. But what if we are not alone? The other category of solutions suggest that they exist, but that there is some reason we don't see them. Perhaps the distances are just too vast, or perhaps they're hiding, either for our protection, the zoo hypothesis, or for their own, the dark forest theory. Or perhaps they are simply too alien for us to recognize. The Great Silence remains the ultimate cosmic mystery, a quiet, profound question mark hanging over our existence. Now let's turn to a paradox that happens not on the galactic scale, but at the very edge of the most extreme objects in the universe. At level 84, we have the black hole information paradox. This is a deep and fundamental conflict between our two greatest theories of the universe, general relativity and quantum mechanics. Let's quietly unpack this. A fundamental law of quantum mechanics is that information can never be destroyed. The unique quantum state of every particle that makes up an object, say a book, must be preserved in some form. But what happens if you throw that book into a black hole? According to Einstein's theory of general relativity, the book is crushed down to an infinitely small, infinitely dense point at the center, the singularity. All the intricate information that made up the book, the arrangement of its atoms, the story written on its pages, seems to be completely and permanently erased from the universe. For a long time, this wasn't a huge problem, because we thought the information was just locked away forever inside the black hole's event horizon. But then, Stephen Hawking showed that black holes are not eternal. They slowly evaporate over immense timescales through a process called Hawking radiation. And his initial calculations suggested that this radiation is completely random and thermal. It contains no information about what fell in. So when the black hole completely evaporates, the information is truly, finally gone. This is a direct violation of the laws of quantum mechanics. Both theories cannot be right. This quiet, beautiful paradox, located at the intersection of the very large and the very small, tells us that we are still missing a fundamental piece of our understanding of reality.
From the edge of a black hole, let's now journey into the strange, bending world of special relativity. At level 85, we have the famous and wonderfully counterintuitive twin paradox. Let's tell this as a quiet story. Imagine two identical twins, both 20 years old. Let's call them Terra and Astra. Terra stays on Earth, while her sister Astra embarks on a journey to a nearby star in a super advanced ship that can travel at 99.5% the speed of light. From Terra's perspective on Earth, the journey is a long one. The round trip takes 20 Earth years. During this time, Terra lives her life, gets older, and waits for her sister to return. When Astra's ship finally lands, Terra is 40 years old. But when Astra steps out of the ship, she has barely aged at all. According to the strange mathematics of time dilation in Einstein's theory, time for her on that fast-moving ship was passing about 10 times slower than for Terra. So while 20 years passed on Earth, only about 2 years have passed for Astra. She is now 22 years old, and her twin sister is a middle-aged woman. Now, here is the paradox. From Astra's perspective on the ship, wasn't the Earth the one that was moving away from her at 99.5% the speed of light? Shouldn't she expect to find that her sister Terra is the one who has aged less? How can they both be younger than each other? It seems like an impossible contradiction. The quiet, elegant solution lies in the fact that their journeys were not symmetrical. Terra, on Earth, has been in a relatively constant state of motion, but Astra, the traveling twin, has not. She had to accelerate to an incredible speed, then decelerate, turn her ship around, accelerate again to come home, and finally decelerate to land. It is this acceleration,
the turning around that breaks the symmetry. She is the one who has physically undergone the journey, and so she is the one who truly experiences less time. It's a quiet, mind-bending truth that time itself is personal and flexible, a river that can flow at different speeds for different travelers.
Now let's revisit a quiet contradiction from our own planet's deep past. At level 86, we have the faint young sun paradox. Our modern understanding of how stars work is very robust. Our computer models can predict with great confidence how a star like our sun evolves over its long, 10 billion year lifetime. And these models tell us something very clear. When our sun was a young star, about 4 billion years ago, when life on Earth was first getting started, it was significantly dimmer than it is today. It would have been only about 70% as luminous as it is now. Now let's think about what that means for the Earth. If our planet were orbiting a sun that was 30% fainter, it would have received much less energy. The average temperature on Earth would have been well below the freezing point of water. Our entire planet should have been a solid, frozen ice ball, a snowball Earth. The oceans would have been frozen solid, and life would have had a very difficult, if not impossible time getting started in such a frigid environment. But when we look at the geological record from that same period, we find the exact opposite. We have ancient rocks, some over 3.5 billion years old, that show clear and undeniable evidence of having been formed in liquid water. We see the fossilized ripples from ancient shorelines, the sedimentary layers from ancient lakes, and special types of rock that can only form underwater. So the rocks tell us that the early Earth was not a snowball. It was warm and wet, and had vast, stable liquid water oceans. This is the faint young sun paradox. The sun was too faint to keep the Earth warm, and yet the Earth was warm. How is this possible? The likely solution lies in the Earth's early atmosphere, which was much thicker and richer in greenhouse gases like carbon dioxide and methane, creating a much stronger greenhouse effect that trapped the faint sun's heat. But the exact balance is a quiet and complex puzzle, a reminder that the habitability of a planet is a delicate and ever-changing dance between its star and its atmosphere.
Our next few paradoxes are not about real objects, but about theoretical ones. The strange ghosts that live inside the equations of physics. They are beautiful, quiet what-ifs. At level 87, we have the concept of a white hole. A white hole is a purely hypothetical object that emerges as a valid mathematical solution to the equations of Einstein's general relativity. It is, in every way, the perfect time-reversed opposite of a black hole. While a black hole is a region of space that things can only enter and never leave, a white hole would be a region of space that things can only leave and never enter. It would be a spontaneous, one-way fountain of matter and energy, with nothing ever able to cross its event horizon from the outside. In some speculative theories, a white hole is imagined to be the exit for a wormhole, or the other side of a black hole in another universe. It's a wonderfully symmetric and appealing idea. However, unlike black holes, for which we have overwhelming observational evidence, most physicists believe that white holes are not physically possible in our universe. The main reason is that their very existence would seem to violate the second law of thermodynamics. A white hole is a highly ordered state that would spontaneously decrease the entropy or disorder of the universe, something that should not happen. Furthermore,
We have no known physical process that could form a white hole. While a black hole is the natural endpoint of a collapsing massive star, there is no known process that would create a spontaneous, outward erupting fountain of matter. So, the white hole remains a beautiful mathematical ghost, a quiet, elegant solution on paper that almost certainly has no counterpart in the real, physical world. This leads us directly to its more famous cousin, at level 88, the wormhole. A wormhole, also known as an Einstein-Rosen bridge, is another tantalizing possibility that arises from the mathematics of general relativity. It is a theoretical tunnel or shortcut through the fabric of space-time, a bridge that could connect two very distant points in our universe, or could even connect our universe to another one entirely.
The idea of a wormhole is the holy grail for science fiction fans, as it would offer a way to bypass the universe's strict speed limit of light and allow for rapid interstellar travel. But, like the white hole, a traversable wormhole is thought to be physically impossible, at least for us. The math shows that as soon as a wormhole forms, it would be incredibly unstable. The immense gravitational forces would cause the throat of the tunnel to pinch off and collapse into a singularity almost instantly, before even a single particle of light could make it all the way through. To keep a wormhole open long enough for something to pass through it, you would need to prop it open with a huge amount of a truly exotic and hypothetical form of matter, something that has a negative energy density. This exotic matter would have anti-gravitational properties, pushing the walls of the wormhole apart and preventing it from collapsing. We have never observed any matter with these properties, and we have no idea if it can even exist. So for now, the wormhole remains a beautiful and quiet mathematical dream. It is a fascinating possibility that emerges from the strange, flexible geometry of space-time, but one that will likely remain forever in the realm of theory and imagination. Now, we return from the purely theoretical to the truly observed. At level 89, we revisit the strange interstellar traveler Oumuamua. The paradox of this object, as we know, was its non-gravitational acceleration. It was moving away from the sun just a little bit faster than it should have been, as if something was giving it a gentle push, but it had no visible cometary tail to explain it. This quiet contradiction has made it one of the most mysterious objects we've ever seen. And at level 90, we have its close cousin in strangeness, Tabby Star. The paradox here is the conflict between its identity and its behavior. It looks like a normal, stable star, but it experiences bizarre, deep, and completely irregular dips in its brightness that we can't explain with any normal astrophysical phenomenon, like planets or comets. Like Oumuamua, it is a quiet, real-world mystery, a unique object in our galaxy that is behaving in a way that our current models cannot yet explain.
All right, we have climbed high into the strange and abstract realms of physics and cosmology. For our final ascent tonight, we will enter the very last gallery of our quiet museum. This is the floor dedicated to the ultimate questions, the most esoteric, philosophical, and mind-bending concepts about the nature of reality itself and its eventual distant fate. We begin at level 91 with an idea that has moved from science fiction to the forefront of theoretical physics. This is the concept of the multiverse. It is not a single theory, but a collection of different scientific ideas that all point to the same incredible conclusion: our universe may not be the only one. One of the most compelling arguments for the multiverse comes from the theory of cosmic inflation we discussed earlier. Some models of inflation, known as eternal inflation, suggest that the inflationary process that grew our universe might not have been a one-time event. Instead, it could be happening continuously, with new bubble universes constantly budding off and expanding within a larger, eternally inflating multiverse. Each of these bubbles would be a self-contained universe, completely isolated from the others, and each one could, in theory, have its own unique set of physical laws and fundamental constants. Another path to the multiverse comes from string theory. String theory requires the existence of extra, hidden spatial dimensions beyond the three we experience. In some versions of the theory, our entire universe is a three-dimensional brain floating in a higher dimensional space called the bulk. The theory suggests that other brain universes could be floating parallel to our own, perhaps only a fraction of a millimeter away in another dimension, but completely inaccessible to us. The quiet, profound implication is that we could be living right next door to an infinite number of other realities without ever being able to know it. The third major path to the multiverse comes from the strange world of quantum mechanics. The many worlds interpretation of quantum mechanics suggests that every time a quantum event with multiple possible outcomes occurs, the universe itself splits into multiple parallel branches. In one branch of the universe, the event has one outcome. In another branch, it has the other outcome. This would mean that there is a constantly branching, near infinite number of parallel universes, representing every single possible history of the cosmos. We have, of course, no direct, testable evidence for the multiverse. It remains a deeply speculative and philosophical idea. But it is a quiet and powerful one. It suggests that reality is infinitely larger, stranger, and more varied than we could ever have imagined. It provides a possible solution to the anthropic principle, suggesting that our universe is fine-tuned for life simply because, in an infinite multiverse, every possible combination of physical laws is bound to happen somewhere. We just happen to live in one of the universes that got the recipe right. From the possibility of other universes, let's now turn our attention back to the stability of our own. At level 92, we revisit the unsettling and deeply strange concept of false vacuum decay. This is the hypothesis that our universe might not be in its most stable, lowest energy state. The vacuum of space itself, this state of nothingness, might be only temporarily stable. Think of it like a boulder resting in a small dip high up on the side of a very tall mountain. It seems stable, it's not rolling down, but there is a much, much deeper valley, a state of much lower energy far below it. The theory of false vacuum decay suggests that the universe is like that boulder. It exists in a false vacuum, and according to the strange laws of quantum mechanics, there is always a tiny non-zero probability that a small part of our universe could randomly quantum tunnel through the intervening mountain ridge and into that deeper, more stable valley.
If this were to happen, even in one tiny spot somewhere in the distant universe, a bubble of true vacuum would be created. This bubble would be a region of space with a lower energy state and
potentially with completely different fundamental laws of physics. And this bubble would be catastrophic for us. It would expand outwards in all directions at the speed of light. As this bubble of true vacuum expanded, it would overwrite our reality. The properties of elementary particles like electrons and quarks, the fundamental forces like electromagnetism, everything could change inside the bubble. As the wall of this bubble passed through you, you would be instantly disintegrated into your constituent fundamental particles and remade into something completely different, governed by a new set of physical laws. The most unsettling part of this idea is that there would be absolutely no warning. Because the bubble wall expands at the speed of light, we would never see it coming. There would be no astronomical signal, no impending sense of doom. One moment, the universe as we know it, with its familiar stars and galaxies, would exist. The next, it would be gone, replaced by a new, more stable, and likely completely lifeless universe. Now, before this idea causes any anxiety, I should say that most physicists believe that if this were a likely event, it probably would have happened already in the 13.8 billion years the universe has been around. Our universe seems to be remarkably stable, but the quiet theoretical possibility remains, a strange and unsettling footnote in our understanding of quantum physics. It is a profound, if unlikely, thought experiment about the ultimate fragility of reality itself.
Now, let's turn our attention from the potentially sudden end of the universe to its most likely and much slower and quieter demise. At level 93, we have the concept of the heat death of the universe. This isn't a speculative what if. It is the most probable endgame for our cosmos, based on the fundamental and inescapable second law of thermodynamics. This law states that the total entropy, or disorder, of a closed system always tends to increase. The universe, as a whole, is moving from a state of order and complexity towards a state of simplicity and decay. The heat death is the story of the universe slowly, gracefully, and completely running down like an old, unwinding clock. The story unfolds on timescales that are so vast, they defy our ability to truly comprehend them. So let's just float through them as abstract ideas. The first era, the one we live in now, is the stelliferous era, the age of stars. It will last for a few trillion years, but eventually all the gas clouds will be used up, and the last stars, even the longest-lived red dwarfs, will finally burn through their fuel and flicker out. The universe will become dark. This begins the degenerate era. The universe will now be populated only by the quiet dead remnants of stars, brown dwarfs, white dwarfs, neutron stars, and black holes. Over an even more immense period of time, these objects will slowly decay. The orbits of planets around these dead stars will be disrupted, and they will be flung out into the darkness. Even protons themselves might, according to some theories, eventually decay, causing all normal matter to slowly evaporate into a thin soup of radiation and light particles. Finally, after a period of time so long that the number is colloquially referred to as a googol of years, we enter the black hole era. The only large organized objects left will be black holes, and even they will not last forever. Through the process of Hawking radiation, they too will slowly evaporate, their mass converted back into a faint, low-energy thermal hiss.
After the last, most massive black hole has finally evaporated away, the universe will enter its final state. This is the dark era. It will be a cold dark and almost perfectly uniform soup of stray photons, neutrinos, and other elementary particles. the temperature will be infinitesimally close to absolute zero. There will be no structure, no complexity, no temperature differences to allow for any work to be done. Entropy will have finally reached its maximum absolute state. And in this state, the very concept of time becomes meaningless. Time is something we perceive through change, through the progression of events. In a universe where nothing ever happens again, time itself, in a way, comes to an end. It is the ultimate eternal quiet, a peaceful, if somewhat melancholy, final fade to black for reality itself. While the heat death is the most likely end, there is a more dramatic, though less probable alternative. At level 94, we have the Big Rip. As we know, the expansion of the universe is accelerating, driven by a mysterious force called dark energy. The Big Rip scenario imagines what would happen if this dark energy is not a constant, but is a phantom energy that grows stronger over time. If this were the case, the accelerating expansion of the universe would become a runaway process. In the far future, the expansion would become so powerful that it would begin to overcome all the other fundamental forces of nature. First, about 1 billion years before the end, the expansion would be strong enough to pull apart the great superclusters of galaxies. Then, a few 100 million years before the end, it would overcome the gravity holding individual galaxies together, and all the stars would be flung apart into the growing darkness. A few months before the end, it would overcome the gravity holding solar systems together, and the Earth would be ripped away from the Sun. In the final terrifying minutes, the expansion would be so violent it would overcome the electromagnetic forces that hold our planet itself together. The Earth would explode. In the final fraction of a second, it would overcome the forces that hold molecules together, and then the strong nuclear force that holds atoms themselves together. The very fabric of reality, every single atom in the universe, would be torn to shreds. It is a violent and complete end to everything. Now we come to our next quiet thought experiment at level 95. This is the bizarre and deeply unsettling idea of Boltzmann brains. This concept, as we've touched on before, comes from thinking about the universe in its final state of heat death. In this cold, dark, and disordered soup that will exist for a near infinitude of time, random quantum fluctuations will still happen. And if you wait long enough, an almost infinite amount of time, then even the most wildly improbable events are not just possible, but are guaranteed to happen. In fact, they will happen an infinite number of times. The physicist Ludwig Boltzmann applied this idea to the concept of consciousness, and the thought experiment goes like this. Which of these two events is more statistically likely? Event A, a random fluctuation in the primordial chaos of the early universe, creates a massive low-entropy state that then evolves over 13.8 billion years through a complex series of physical laws to create a vast structured universe, a galaxy, a star, a planet, and finally, your own complex, self-aware brain that is capable of reading this and having this thought. Or Event B, in the far, far distant high-entropy soup of the heat death, a random fluctuation momentarily brings together just enough particles in just the right configuration to form a single, self-aware human brain, complete with a full set of false memories of a life it never lived and a universe that doesn't exist. which has the exact same thought you are having right now, before it instantly dissolves back into the chaos. The deeply unnerving answer from a purely statistical point of view is that event B is vastly, incomprehensibly more likely than event A. This leads to the philosophical paradox. If this is true, then how can you be sure that you are not a Boltzmann brain? How can you be certain that your past is real, that the world around you is real, and that you will still exist in the next moment? It's a quiet, dizzying puzzle that uses the laws of thermodynamics to question the very foundation of our perception and our existence.
From this strange philosophical puzzle, we now turn to what is perhaps the deepest and most intimate mystery of all. We are at level 96, the nature of consciousness. This is not strictly a cosmic concept, but it is the filter through which we experience the entire cosmos, and its origin is a profound scientific mystery. It's what philosophers call the hard problem. We know, on a mechanical level, what the brain does. It is an incredibly complex biological computer. It processes information from our senses, it stores memories, and it controls our actions. We can map the neural pathways, we can measure the electrical signals, we can see which parts of the brain light up when we feel a certain emotion. But how does all of that purely physical, electrochemical activity create the rich, subjective, inner experience of being you? How does the firing of neurons in your visual cortex create the experience of the color red? How do vibrations in the air processed by your auditory nerve create the feeling of listening to a beautiful piece of music? How does a collection of atoms and molecules give rise to the feeling of love, or sadness, or wonder? This is the explanatory gap. There is nothing in our current understanding of physics, chemistry, or biology that even begins to explain how subjective, first-person experience emerges from objective physical matter. Is consciousness a fundamental property of the universe, like mass or electric charge, that exists in everything to some small degree? Is it an emergent property that only arises when a system, like a brain, reaches a certain level of complexity? Are we just incredibly sophisticated biological machines with a powerful illusion of an inner self? The quiet truth is, we have no idea. The mystery of our own awareness is perhaps the greatest mystery we will ever face. At level 97, we have another quiet, philosophical puzzle that sits at the intersection of our minds and the universe. This is the mystery of the unreasonable effectiveness of mathematics. The physicist Eugene Wigner wrote a famous paper on this topic. He was struck by a profound and deeply strange fact. The abstract, man-made concepts of mathematics seem to describe the physical universe with incredible and often completely unexpected accuracy. Think about it. A mathematician can sit in a quiet room and, using only pure logic and imagination, develop a new kind of abstract geometry or a new set of equations. And then, decades later, a physicist studying the universe will find that this exact piece of abstract mathematics perfectly describes a real-world physical phenomenon, like the curvature of space-time around a black hole, or the behavior of a quantum particle. Why should this be the case? There is no obvious reason why the universe should be comprehensible to us, or why it should follow elegant, beautiful mathematical laws that we are capable of discovering. Is it just a happy coincidence? Is it that our brains themselves have evolved to recognize the inherent mathematical patterns of the world we live in? Or does it hint at something much deeper?
Does it suggest that the universe itself is, at its most fundamental level, a mathematical structure, and that our minds are, in a quiet way, just uncovering a pre-existing cosmic code? It's a profound question about the deep and mysterious connection between human thought and the fabric of reality. Now we turn to our next idea at level 98, the nature of time. We experience time as a fundamental part of reality. It feels like a river flowing constantly forward in one single irreversible direction, carrying us from the known past through the fleeting present and into the unknown future. But many modern theories in physics suggest that this deeply intuitive experience of the flow of time might be just a powerful and persistent illusion, a product of our human consciousness and our perception of entropy.
In Einstein's theory of relativity, for example, time is not a flow, it is a dimension. It is woven together with the three dimensions of space into a single four-dimensional fabric called spacetime. In this block universe view, the past, the present, and the future all exist simultaneously and are equally real. The entire history of the universe is a single, static, four-dimensional block. Our feeling of time passing is just our consciousness moving along our particular world line through this pre-existing block. The future is already there, just as the past is. In quantum mechanics, on the other hand, time is treated very differently. It's not a dimension, but a universal external parameter, a background clock against which quantum events unfold. This fundamental disagreement about the nature of time is one of the key reasons why general relativity and quantum mechanics are so notoriously difficult to unify into a single theory of everything. So which is it? Is time a real flowing river, as our intuition tells us? Or is it a static dimension that we just happen to perceive as moving? Or is it, as some more advanced theories suggest, not fundamental at all, but an emergent property that arises from some deeper, timeless quantum reality, much like temperature arises from the motion of individual atoms? The quiet truth is, we do not know. The most familiar and fundamental aspect of our own experience might be the universe's greatest illusion. Our journey up the ladder is almost complete. We have reached level 99, the unobservable universe. This is not a theory, but a simple, factual consequence of the age of our universe and the speed of light. As we know, the universe began about 13.8 billion years ago. This means that the absolute farthest we can possibly see in any direction is 13.8 billion light years. This sphere around us, with a radius of 13.8 billion light years, is what we call the observable universe. It is our cosmic horizon.
But there is absolutely no reason to think that the universe just stops at the edge of what we can see. The universe beyond our horizon is likely just more of the same. More galaxies, more clusters, more voids, stretching on and on. But we can never see it. The light from those distant regions simply has not had enough time in the entire history of the universe to reach us yet. And the situation is even more extreme than that. Because of dark energy, the expansion of the universe is accelerating. This means that galaxies that are very far away are receding from us faster than the speed of light. Again, this doesn't violate relativity, as it is the space between us and them that is stretching, but the consequence is profound. The light from those galaxies is like a person trying to run up a downward-moving escalator that is moving faster than they can run. They will never reach the top. The light from those distant galaxies will never, ever be able to reach us.
This means that the edge of our observable universe is, in a very real sense, shrinking. We are losing the universe. Galaxies that we can see today in our most powerful telescopes will, in the far, far distant future, cross this cosmic horizon and disappear from our view forever, their light no longer able to outrun the expansion of space. It is a quiet, profound, and inescapable form of cosmic isolation. We are fundamentally and permanently cut off from seeing most of reality, trapped inside our own small, finite bubble of observation. And now we have arrived at our final destination. We are at level 100, the unknown. This is not a concept or a theory. It is a quiet, humble acknowledgement. After all our exploration, after all our incredible discoveries, after climbing 100 levels of cosmic understanding, we arrive at the most profound realization of all, that the universe of our knowledge is just a tiny, sunlit island surrounded by a vast, dark, and endless ocean of our ignorance.
For every question we have answered, a dozen new and stranger questions have appeared. We have learned that our universe is made of 95% dark matter and dark energy, and we have no idea what either of those things are. We have learned that our reality might be a projection from a higher dimension, or a simulation in a vast computer, or just one of an infinite number of other universes. We have learned that the beginning of time and the heart of a black hole are still complete mysteries to us. We have learned that the sky is quiet when it should be loud. The more we learn, the more we realize how little we truly know. And that, I think, is the most beautiful and most calming thought of all. It means the journey is endless. The adventure of discovery will never be over. There will always be new mysteries to ponder, new puzzles to solve, and new, breathtaking vistas of reality to uncover. The greatest terror of all might be the idea of a universe that is small enough for us to completely understand. But the universe is not small. And it is not simple. It is vast and strange and beautiful and deeply, wonderfully mysterious. So as we conclude our long ascent tonight, let your mind be at peace. Let it float in the quiet, comfortable space of not knowing. We have traveled from the simple reality of our own planet to the very edge of theoretical physics and philosophy. We have held some of the biggest ideas the human mind has ever conceived. And now, it is time to let them go. Let them drift away, like faint stars in the quiet of the night. The universe will keep its secrets for another day. And tonight, our journey is at an end. It is time to rest. Sweet dreams.